Example, the displacement x versus time t for 2.5 kilogram mass on a spring having a spring constant k equals to 4 Newton per meter is shown in the sine graph. A. Find the period and the frequency of the motion. As we know, the period is the time taken for one complete oscillation or cycle, that is 6 millisecond. We have to take a look at the unit, and 6 millisecond is 6 times 10 to minus 3 second. And frequency equals to 1 hour period, that is 1 hour 0.006. that gives us 170 hertz in two significant figures. B. Find the amplitude of the motion. Amplitude is the maximum displacement, that is 2 millimeter, that is 2 times 10 to minus 3 meter. C. Sketches a graph of displacement versus time for a situation where amplitude is cut in half. For simple harmonic motion, the period is independent of the amplitude, so period stays the same, 6 millisecond. But amplitude, it becomes half, which is 1 millimeter. And we have the graph. Blue graph shows an equivalent system in simple harmonic motion. What is the phase difference between red and blue? So let's take a look at the following graph, the displacement time graph, and we have the angles, 0 degree, and here we have a 90 degree, 180 degree, here we have a 270 degree and 360 degree. So one complete oscillation represented as a 360 degree. Let's take a look at one cycle. In this case, one cycle is 6 millisecond or 6 unit. So one cycle is 6 unit, which means 6 unit is 360 degree. Let's place the blue and let's see the difference. That is 1 unit. So the phase difference is 1 unit out of 6 unit. So 1 over 6 times 360 degree, because 6 unit is 360 degree. So 1 unit equals to 60 degree. So phase difference is 60 degree. Let us convert that into radian. 60 degree times pi over 180 degree. That gives us pi over 3 radian. We see that t over 6 equals to 360 degree divided by 6. That's a 60 degree, and that is 2 pi over 6 radian, or pi over 3 radian. Example, the displacement x versus time t for system undergoing simple harmonic motion is shown here. Sketch in red the velocity versus time graph. At extreme positions, if you look at the animation at the top, at extreme positions, velocity becomes 0. There. We have the 0 points there. When at displacement equals to 0, velocity is maximum. So slope determines sign of maximum velocity. Positive slope, positive velocity. Negative slope, negative maximum velocity. Positive slope, negative, positive, or positive slope, negative slope, negative, positive. The slope determines the sign of maximum velocity, but with different scale. So we have positive value. Here we have negative. Positive value, as the slope is positive, slope is negative, negative velocity. Slope is positive as a positive slope. Then we have our graph. Sketch in blue So acceleration versus time graph. Acceleration versus time graph is quite simple, as we have the defining equation. Acceleration is proportional to displacement in opposite direction. A is just a reflection, or acceleration is just a reflection of displacement, like that. And red is cosine, and acceleration is minus sine waves. Example, the kinetic energy versus displacement for a system undergoing simple harmonic motion is shown in the graph. System consists of 0.125 kilogram mass on a spring. Determine the maximum velocity of the mass. From the graph, you can see that kinetic energy is maximum, the velocity is also maximum. And maximum kinetic energy is 4 joule. So, we equate 4 equals to 1 over 2 times mass times maximum velocity squared. So that 4 equals to 1 over 2 times mass 0.125 times maximum velocity squared. And maximum velocity equals to 8 meter per second. Sketch EP and determine the total energy of the system. As we know, total energy is the sum of the kinetic and potential energy, which is constant. And since potential energy is 0 when the kinetic energy is max, it must be that total energy equals to maximum kinetic energy, which is 4 joule. And potential graph will be the inverted kinetic graph. However, we need to pay attention to the crossing point. Potential is 2, kinetic is 2. 2 plus 2 still gives us 4 total. Here too, kinetic is 2 joule, potential is 2 joule. 2 plus 2 gives us total 4 joule. C. Determine the spring constant K of the spring. We utilize the elastic potential energy formula, which is equals to 1 over 2 spring constant times displacement squared. We also note that kinetic energy is 0 when the displacement is maximum. Kinetic energy is 0 when the displacement is max, which is equals to 2 centimeter. Therefore, EK plus EP equals to ET, and ET equals to kinetic energy 0 plus the maximum potential energy is 1 over 2 kx max squared. So the total energy is 4 equals to 1 over 2 times the spring constant times the maximum displacement or amplitude 0.02 squared. K equals to 20,000 Newton per meter. That's a spring constant. D. Determine the acceleration of the mass at x equals to 1 centimeter. From Hooke's law, F equal to minus kx, and we have F equals to spring constant is 20,000 times the displacement 1 centimeter, which is 0.01 meter. So that gives us minus 200 Newton. And from Newton's second law, F equals to ma, we get F equals to minus 200 equals to mass is 0.125 times acceleration, and acceleration is equals to minus 1600 meter per second per second. 4 kilogram mass is placed on a spring's end and displaced 2 meter to the right. Spring force F versus its displacement x from equilibrium is shown in the graph. A. How do you know that the mass is undergoing simple harmonic motion? We look at the defining equation for simple harmonic motion. In a simple harmonic motion, acceleration is proportional to displacement but opposite direction. Since F equals to ma, then force is proportional to displacement but opposite direction as the mass is constant. And now let's take a look at the graph. Graph shows F proportional to displacement but opposite direction. Therefore, we have simple harmonic motion. B. Find the spring constant of the spring. We're going to use Hooke's law. f equals to minus kx. Pick any f and any x. We pick this point. Force is minus 5 Newton and displacement is 1 meter. And k equals to minus 5 divided by 1. So that's 5 Newton per meter. C. Find the total energy of the system. From the graph, we know the maximum displacement or amplitude. Then we utilize the elastic potential energy formula. EP equals to 1/2 kx squared. And when the potential energy max, the kinetic energy becomes 0. So the total energy equals to maximum elastic potential energy. So total energy equals to 1/2 times spring constant times the amplitude squared, which is equals to 1/2 times spring constant is 5 and amplitude is 2, and we squared, we get 10 joule. D. Find the maximum speed of the mass. We know the total energy from the previous slide. When the kinetic energy is maximum, elastic potential energy is 0. And the maximum potential energy equals to maximum kinetic energy, which is total energy. So use ET equals to 1/2 mv max squared. Total energy is 10, which is maximum elastic potential energy, which is also maximum kinetic energy. 1/2 times mass is 4 times maximum velocity squared. And maximum velocity equals to 2.2 meter per second. E. Find the speed of the mass when its displacement is 1 meter. When displacement is 1 meter, we have kinetic energy as well as elastic potential energy. And the total energy is unchanged, which is 10 equals to 1/2 times the mass 4 times the velocity squared plus 1/2 times spring constant is 5, and the displacement it shows 1 meter, 1 squared, and the velocity equals to 1.9 meter per second.